So if I throw a ball at a wall, I expect it to come back, right? But in quantum, there were particles that were going through the wall. So all this is phenomena which is very new, which one cannot uh, explain using a common intuition of the world that we live in.
Welcome to the PAM Talks. Each episode, we interview a new physics and astronomy mentor, exploring the universe through the lens of diversity. I am Emina Hafiz, and today I will be your host. I am an undergraduate student in astrophysics at the University of Calgary. In this episode of PAM Talks, we're diving into the fascinating world of quantum computing with our guest mentor, Pragati Gupta, a PhD candidate from the University of Calgary who is part of the Quantum Science and Technology Group in the Department of Physics and Astronomy. Quantum mechanics is a physics theory that started to be developed in the early 20th century. Any of the older physics ideas that came before this time are called classical theories. Quantum mechanics describes the behavior of matter and energy at the smallest scales, typically at the scale of atoms and subatomic particles like electrons. One of the central ideas of quantum mechanics is wave-particle duality. This is the idea that something can have both wave and particle properties. Waves spread out and can be everywhere at once. And when a particle acts as a wave, it can be in two different, even completely opposite states at the same time. This is called superposition. In quantum theory, when electrons act as waves, they can be in multiple locations at once. Quantum computing is a developing technology that leverages the principles of quantum mechanics to make computers that will be able to rapidly solve some of the types of problems that are challenging for classical computers to solve efficiently. Instead of using classical bits, quantum computers use quantum bits, or qubits. What makes qubits special is that they can exist in multiple states at the same time. It's like having a light switch that can be both on and off simultaneously. This property is an example of superposition. Because of a superposition, a quantum computer can perform many calculations at the same time, making it potentially much more powerful than a classical computer for certain types of problems. Quantum computing is a rapidly growing field of research, and in this episode of PAM Talks, our mentor Pragati will tell us her research in quantum computing. This is the PAM Talks, where the universe is as diverse as the minds unraveling its mysteries. Coming up next, my interview with Pragati.
Hi, I'm Pragati. I'm a PhD student at the University of Calgary. I'm in my second year. I am a student in the Quantum Science and Technology group. I work on quantum computation and designing how quantum mechanics can be used to build something nice and cool.
That does sound very cool.
Yes.
How did you, what sparked your interest into going into quantum computing?
I met a person who told me that people are building really powerful computers that could break into codes. The idea is to build codes that are safe against those powerful computers, but also to build computers that could break the code. So it's a fight that was going on between the two parties. So that's what got me interested into quantum computation.
That is very cool. Thinking about trying to break into codes and figuring out ways to prevent that and all that.
Yes.
So what would be your best definition about what quantum is and how we are able to actually use it in a computer, how you're talking about you're doing quantum computing, how does that work?
Quantum came in at a time when people believed that all of physics was over. We know everything that was there to know. And then at that time, some experiments showed that what we predict using our classical understanding or our common sense is not really working. So there are objects at a big scale that we see, like a ball, a table, or anything that we see in the real world. And then there are objects they're very tiny that make up these big objects.
Okay, so macroscopic objects, classical, and then tiny things, quantum.
But when you go down to the very tiniest of particles, like an electron or a proton or something like a nucleus or an atom, then it's hard to find where that particle is. And it's not just because there aren't enough instruments to measure the particle's position at that small scale, but it's also because it's fundamentally not defined where that particle would be. So this is the difference between what's quantum and what's not. In a quantum mechanical world, something could exist both as a particle and as a wave. For example, in a water wave, you would expect that a water wave would sort of spread across in space, and you should be able to measure the wave at different positions. But what's happening in quantum is that the particle is spreading on all over the space, but the moment you measure it, it's at one. So how we interpret quantum mechanical phenomena is by measuring the object again and again and seeing whether it's only at one position or whether there's a probability of observing it at different places.
All right, that is very cool. How would you describe how you are able to use it for computing? Like, what does quantum computing mean?
So all the computation that we do right now, the calculations are based on binary, which is zeros and ones.
Mhm.
So basically, you can think of it as a switch, which you turn off or on. And then a lot of switches tell you something about the state, like it's an information you code in those switches.
Mhm.
Now, just imagine, for example, if you have a switch, but it could be both on and off at the same time, which means that you could explore the option like zero at the same time as well as one. So that gives you a lot more power. And that comes back to the superposition that a thing could be at two positions at the same time. So I would interpret the particle being at one position as one state and the particle being at another position as at another state. And in the quantum mechanical world, it's traveling on both the paths.
So you mentioned that they are faster. Do you have kind of like approximately how much faster it is? Like for us to be able to switch from classical to quantum computers and understand the benefits from them, like how much of a difference does it really make in the time?
So our computers have a limit of the number of bits that they can encode. So how big a number, for example, you can think about on a computer at the same time. So all our encryption schemes just assume that we have a big enough number
Mhm.
and that nobody has enough power to crack that number.
Mhm.
So the fact that, say, you and I can talk and hope that somebody is not eavesdropping is just reliant on how big the number is.
Okay.
Now, for a quantum computer, that would take a few seconds to find that number.
Mhm.
So, and on our current supercomputers, that would not be possible in the age of this universe.
Oh wow, so that is definitely a very big difference. All right, you're able to compute something using like two things at the same time instead of doing two separate operations for them, then it makes it faster.
Yep.
Like, are there any other benefits to being able to quantum compute?
So, quantum computation was actually proposed by Feynman in 1982. And he said that if we really want to understand nature, we should be able to simulate quantum mechanical behavior. And the moment you try to do it on a normal computer, you soon find that it's impossible to study anything which is of reasonable size. So, apart from it having applications for doing faster computation, it would make it possible to understand a lot of physical phenomena which we cannot understand. So, for example, calculations of how a lot of particles interact, something called many body physics, is not possible on our current computers. We just can, at best, approximate some behavior, that too in a theoretical limit. So the problem becomes so large that even the best of the supercomputers would take a lot of time to solve something like that.
So that's very interesting, and it sounds a lot like, I guess, I mean, quantum, especially nowadays in media, is a very like, I want to say well-known word, not because people understand the definition, but it's just used everywhere for everything, like in Marvel and in science and sci-fi and everything. So like when we're talking about it in this kind of case, like how tangible are these things? Like, do we have a working quantum computer?
Oh yes, there are not just one, but quite a few quantum computers now, and they are doing calculations that we do on classical computers, but they're doing them using a very different phenomena altogether. They're using something called superconducting qubits. So there are quantum computers that are being built and being used all over the world now, and it's not just in textbooks anymore. Like we think of most of the science that it's an academic interest. It's something which most countries want to fight for now to build it, and there's a lot of interest because of the potential that it has.
So for your research specifically, can you explain a little bit more about the things that you do?
So my specific research has to do with controlling phenomena in atoms, that is like electrons or the nucleus to build a quantum computer. So the atom has a natural way of evolving. But that does not help us because in a computation, for example, you would want to add two specific numbers. You don't want to add any number. So, for example, the electron is in a particular state, and then to do a quantum computation, I want to make it go on a particular path, or I want to make it go on two particular paths at the same time. You see that in nature, but how do you make that happen so that you know exactly what would happen and when that would happen? So that's where I come in, that I design controls and design the physics, how the interaction of the atom can be controlled to make the atom do a particular calculation.
So, are there specific types of atoms or nuclei that you need to use for these things, or can you just use anything? Like, how specific and like rigorous does the process actually have to be?
The periodic table explains the number of free electrons an atom has, the number of electrons that can be excited, or the number of electrons that are paired up, which cannot be excited that easily, and so on. Depending on the model of quantum computation that you use, we make use of specific atoms. I only deal with the elements of the first group, which are rubidium, cesium, which have just one free electron. But having more than one electron makes them hard to control because the electrons start interacting with each other. So, though I want a lot of quantum mechanical behavior, but I also want to make sure that I can control each part of it. And then having more electrons on the outside makes them hard to control. So, we want just enough quantum behavior, but not too much that it goes out of control.
That is very cool. So, I mean, again, branching off of the thing of we hear a lot about quantum, but because people don't really understand it all the time, sometimes we look at it and think it's kind of a completely like unattainable like position to be able to get into quantum. Because I know, at least for me and a lot of my friends, going to physics was something that wasn't like an automatic choice either. It was very much like you have to build up a lot of confidence before you go into this kind of field. And with a lot of science too, but especially physics seems like the more isolated one, where they reserve it for Einstein and Newton and all of these figures who are like just beyond.
Yes, I think they build up this aura to make it popular, but
It just makes it scary and intimidating.
exactly, that's what I hate about. I mean, it's good to have a good sci-fi movie, but at the end of the day, people think that it's not possible because they're not that character; they're the other. They end up being villains instead. So I and that it honestly did stop me a bit as well from taking up physics. So when I was in undergrad, the gender ratio was very bad. So the number of girls. So in a batch of 100, there were just about 10 or less, 10 or few girls. And there was a common conception that we would all end up taking maybe biology or chemistry, but we shouldn't be doing maths or physics. It did make me question myself. I always believe that scientists aren't humans, and there's something that's going on that I don't know and I can't know. It's something which is beyond understanding. But as I have like seen and talked to people and also went through the courses, and I had good examples to look at in history, I realized that it's much easier than what we portray in media or in the movies, that scientists are people who have some supernatural powers to understand whatever is in front of them, or to build something powerful, or to solve all the world's problems. But that's not true. We try to understand and to ask questions, but what's really that all that's needed is just a curiosity and the fact that to accept that we don't know.
No, it's very reassuring to be able to hear that too, because like yeah, I know what you mean about. There's always the conception that if women were to go into science, it's always something biology related, medical related, chemistry sometimes too,
Yes,
but
exactly.
physics is always unheard of.
Yes.
But it's yeah, you're right. There's so many good examples of like women in physics who do amazing things and who are continuing to as well. So I hope that more people start to go into it as well and realize that it's not something that needs to be restricted.
Yeah.
In terms of like building up the background to be able to do something in physics, just generally. Like, because I mean, you mentioned, of course, there's a lot of math that's in physics, but even like maybe for students who are in high school and they struggle a bit with math, or they struggle sometimes with like the more classical physics concepts or something, like, do you have any advice for them going into this? Like, do you need to be like, I know we just talked about you don't need to be a genius to necessarily do it, but like, what do you feel about like, what are the important skills that you need to be able to be a physicist?
Um, the most important skill is to be able to visualize what's happening. I would even today I can't. So do I said that quantum mechanics is to deal with shut up and calculate? I can't do that. So for me, I have to be able to think that okay, if I'm even for very classical stuff, very simple stuff, just the fact that, for example, say there's a car which is traveling. I need to close my eyes, shut my eyes, and think, okay, there's a car that's moving, and I want to see how fast it's moving. So maybe I want to check how far it has traveled in a particular time. So the basic to be a scientist or to be a physicist in particular, I would say, is that to be able to visualize what you're studying. To, for example, we see all these word problems or like descriptions of a problem in an exam, and then eventually we just end up writing some equations to solve it. But if you think that you can see what's happening even though you don't know how to write an equation, I think that person makes a very good physicist.
I think we only have time for one more question. So, if a young person hearing this interview finds themselves interested in quantum computing, do you think that there will be career opportunities for them now or in the future?
Yes, and it's more it's like quantum is just going to boom these days. It's not going to go down for some time. So and hopefully by then we'll have a quantum computer. So it's going to lead to a lot of opportunities, very unconventional ones. So the good part about quantum science these days is there are so many jobs opening up. In fact, there are talks that there aren't enough people as there are a number of jobs in quantum. So taking up a career in science today is more exciting than it has ever been.
I'm glad. That is really exciting to hear. Well, that's the end of this episode of the PAM Talks. Thanks so much to Pragati Gupta for joining us. Stay tuned for our next episode, where E. Thompson will interview Jenny Lawson, a PhD student in mathematics at the University of Calgary. Get ready to explore the universe through the lens of diversity and join us in celebrating the brilliant minds breaking barriers in physics and astronomy. The PAM Talks gratefully acknowledges the support from the University of Calgary Graduate Student Association Quality Money Grant Program.